physics. So Cheng and I would like to share these last 20 minutes or so of the session to tell you about the influence that Steve has had. And for myself, I can say that at every important scientific juncture, at my life, at almost every such juncture, it was Steve and his work that influenced me. So things started out when I was an undergraduate student in Munich. I had done some work in the nuclear physics labs, and I was looking for a diploma thesis. And at the time, I had heard about somebody called Ted Hensch, who had arrived from Stanford to Munich a few years earlier. And somebody described this as somebody who was doing precision measurements at the 10-digit level. And little did I know, so my first thought was, oh, it must be incredibly boring to measure one more digit of some number. So I pretty much took that off my list. And then by mistake almost, I wandered into one of Ted Hensch's seminars, and Ted was speaking about something I didn't really understand very much. You could somehow dress atoms, and there were detunings, and red and blue, and so on. But what I could understand is that somebody had done an experiment where he had trapped atoms in a light field. These were 500 atoms, and this is, of course, the famous 1986 optical dipole force paper. Gee, I thought this is really interesting. So I decided to do a seminar in the Hensch group, and he offered me a list of about 30 papers to choose from. And when I looked through them, I decided to do this paper. Again, I didn't know its significance, but I thought, wow, you can laser cool the atoms. And this is the paper from the previous year, the optical molasses paper from 1985. I would like to point to this number here, 240 microkelvin. If Steve had written down here the number that they actually measured in the lab, I guess Bill Phillips would still be famous, but maybe he'll say a few words about this evening. So this is one of the instances where the experiment went better than anticipated. So this was the first atomic physics paper that I have ever read. So, you know, with these standards, I should maybe just mention there was, from these 3 marvelous years, there was the 1987 paper, the magneto-optical trap mod, where they basically went from a few hundred atoms 2 years earlier to 10 million atoms. And this, of course, as you all know, has become the workhorse of cold atom physics and has redefined the atomic physics field. At this point, I had done my diploma thesis, I was into my graduate work, and I decided to deviate from Steve's path. Steve was a champion of optical dipole traps. I decided, however, to follow the lead of some more obscure groups, somebody named Ketterle and Hewlett, and then some people named Cornell and Wyman. Sorry, Carl, I didn't know you were famous at that time, as famous as Steve, at least. So they had these techniques, and so decided it would be really cool to build a magnetic trap. And maybe it was lucky that I did it, because this attracted, as we shall see in a moment, Steve's attention. So this is one of the things that we built at the time. I was really interested in making very high gradients, very steep traps for high collisions. And what we did here is we had a permanent magnet embedded in a magnetic material here with an electric, with a coil outside here. And then I sharpened a steel tip here to a radius of something like 10 micrometers on the lathe, which gave us these gradients of 30 Tesla per centimeter, and where we could trap atoms, lithium atoms in that system. At about that time, Steve had won the Humboldt Prize, and part of this prize was to spend a few months as a guest in Ted Hensch's group in Garching. So when Steve arrived, the first thing he noticed was, of course, the very lax work ethics of the Europeans, because most graduate students in August were on vacation. So I was one of the few who weren't there, and when I told him a little bit about this experiment, he said, well, why don't we go on and calculate? This is really interesting to miniaturize things. Maybe we can put wires on a chip and calculate what the fields are. So at the time, I had a program that allowed one to calculate 3D magnetic fields for a structure of wires and so on. So that was very interesting. I said yes. So Steve, who was living in Garching at the time, every day would come over, and then we would start to talk physics, talk about these traps and so on. However, before we could come to the interesting part, namely physics, we had to talk about something else first. Which brings me to Stephen Paganini. So, besides the obvious resemblance, Niccolo Paganini was a famous virtuoso on the violin of the 18th century. He had these incredible violin solos, and so one anecdote is that after one marvelous concert, some admirer came to him and she said, "Maestro, how did you do it? It was wonderful. I cannot believe it." And he was rather impatient first. He said, yes, of course I played well. But did you see how elegantly I bowed to the audience? So I have often thought that Steve felt the same way about his sports accomplishments. So what it meant is that usually before we would start talking about physics, we would talk about how fast he could bike. So Steve, having come from Stanford, where he was used to these extensive bike tours in the beautiful hills around Stanford, was missing his sports activities. And so he said to Ted Hensch whether it would be possible to organize a bike for him, whether MPQ, the Max Planck Institute, could provide a bicycle for him so that he could work out and so on. Ted Hensch says, of course, no problem, I'll arrange it. So Ted Hensch spoke to Frau Lechner, his secretary, and the very next day a bike arrived. I'm not joking, it was a pink lady's bike. So Steve's disappointment was not this one. This is a picture from a different context, but he was not so happy. In any case, I never found out whether this was something that had to do with Ted Hensch's peculiar sense of humor. And if you think of Ted Hensch in sports, you will know what I mean. Or whether Frau Lechner acted on her own initiative. But in any case, this is the official MPQ bike. But I can assure you that Steve was the fastest human who to ever travel the 15 miles from Garching to Munich on a pink lady's bike. So we calculated magnetic microtraps. We were very proud. We thought we had invented them. Then Klaus Zimmermann pointed out to us that already in 1991 or so, somebody at Caltech named Liebrecht had written a paper. But it sounded like an interesting thing to do, so Steve invited me as a postdoc to Stanford to work on magnetic microtraps. However, when I arrived, this is, as we have heard, a famous trick of his, he suggested that maybe for a few weeks or months I would work on some other experiments on optical dipole traps that we had, and I think at this point Cheng will take over and tell a little bit about what you've done.
Thank you. My name is Chen Chin. Okay, before I start continuous Vladan story, I'll tell you a little bit about myself. Okay, this one is supposed to be yours. Okay, I joined Steve Chu in the September 1995. Okay, and it's a in contrast to Vladan, that he already has some basic knowledge on atomic physics. When I joined Stanford, and when I went to his office, I knew nothing. I was essentially a blank, say a piece of white paper, and I had no experiment skill. I haven't even I don't even know how to use a soldering iron. Everything. Okay, yeah. But however, I went to his talk. Okay, Steve's talk was so amazing, and talk about all kind of exciting applications. The thing that I really remember is he mentioned that once you can plot the local gravitational constant, okay, then people use this kind of local G management. They can re-identify the meteor impact site in Mexico Bay. Okay, that's how they identify that site. And at that time, I thought, wow, that's so fantastic. You can really have application of something like this. And I'm seeing myself, one day I may really hold some device and go out and search for a dinosaur or something. Okay, well, that didn't happen. Okay, but I joined the group in a very exciting period. Okay, I will call it the second phase of Steve research. Okay, well, what I mean is that when I joined the group, about 80% of people in Steve's group working on atomic physics and 20% on biophysics. But when I graduated, just the other way around. Okay. And this picture was taken essentially around the transition point in '97. Okay, that's you can see this. Steve got Nobel Prize in October 20 in December 1997. Okay, and this was a picture taken a few months after that, so that's why Steve is smiling. Okay, now, I'm also smiling. Okay, I'm happy for him. Okay, but little did I know that starting from that day, I had to share my advisor with the rest of the people in the world. Okay, so I joined the group in the beginning to work on this kind of precision measurement to search for electric dipole moment based on cesium atom. So this is a kind of this is the chamber. I think like almost the third generation of chamber we made. Eventually, didn't do any of this, any of the precision measurement. But you can see from this picture, we try to make everything small and compact. Okay, we worry about the magnetic field will leak out, will cause us systematic error. Okay, And during the construction, actually, before Steve got the prize, I really learned. Steve really came to the lab, really told me, for example, a few occasions, told me how to do the drilling, how to you really led me to the machine shop and told me how to do a few things. Okay, I really appreciate that. And also showed me how to operate the camera. Okay, and I'm not sure this is the third occasion. Okay. Anyway, so with in the beginning, that's how our experiment. That's the plan of the experiment. Okay, and but very quickly, we knew we'll be on our own. Okay, and the first 2 years essentially were in the basement of variant building. Okay, pretty much to what similar to what Steve described himself. Okay, in Berkeley, in the Berkeley time, that he considered himself it's kind of more in the underground. Okay, and at that time, Jamie Kerman, my partner, and myself were also working in the basement. Okay, for 2 years. We also feel we don't recall consider with moths. Okay, but we consider with mummies. Okay, mummies hiding under the pyramid. Okay, all right. But before we really were really ready to do any precision measurement to search for electric dipole moment, okay, what we found is something really strange. We load this atom into the dipole track and try to characterize, try to see how well they reach a thermal equilibrium, okay, and try to characterize the behavior of the particle in the cesium atom in the dipole trap. Okay, here we found this. I think this. We found essentially the collision rate turns out to have a very strong dependence on magnetic field. Okay, and that's pretty exciting that in that time. Okay, it's the field prediction by Bahar. Okay, showing that there could be some dependence of the collision properties. Okay, as a function when you change the external magnetic field. And what is shown here, okay, on the experiment side, the data experiment side, is essentially reflects the elastic collision of atoms, cesium atoms, at different magnetic field. At certain magnetic field, the collision rate essentially drops to 0. And then, in that case, the system more or less is a pretty much ideal gas. Okay, for those people who are not physicists, when physicists talk about ideal, that means boring. It's a boring gas limit. On the other hand, if we go to other magnetic field, then the cross section of the system, later the theory, they feed out data using these resonant positions. Okay, they determine the cross section can be as large as 1 × 10 to minus 10. Okay, if you take the square root of that, that means the size of the atom effectively is about 100 nanometers. It's enormous. Okay, several order mean to larger than the actual size of the atom. It took several years for us to fully understand what's really going on. Okay, in the collision of the cesium atom. Okay, and also during that time we have a lot of idea what to do with this collision and what we can what kind of physics we can really explore. This is essentially a new type of kind of physics we didn't expect earlier. Okay, so after many years of study, now this phase bar resonance becomes my main interest in the world of quantum gas. Okay, so here I'm showing how scattering behaves, how scattering varies as a function of magnetic field. Okay, normalized to the width of resonance, and the scattering length itself determines how large the cross section is. Okay, and what happens is that a certain kind of magic value, the magnetic field getting close to the resonant position. Okay, then the scattering diverges. It diverges in a very universal way. Okay, and that's associated with the fact that the molecular state can be brought into the continuum. So, why the magnetic field can induce this kind of resonance because of our atomic molecule in general they can have different magnetic moment. So two states with different magnetic moment can always be brought into resonance by external field. And why is this interesting? Because now essentially we found out a new tool to change the interaction. The interaction characterized by scattering length. Okay, and you can change the interaction to different regime. For example, if you go to this point when the scattering goes to 0, that essentially shows you there will be zero interaction. Okay, there will be zero interaction. And go to also larger scattering lengths, then that will be the system will be very, very interesting, exciting. And the phase bar resonance was first realized at MIT in '98, but we found the resonance in '99, and essentially we discovered all the resonance. We essentially opened the research in cesium resonance, and within a few years we characterized all the resonance and we pinned down the interaction parameter. Okay, so that we determined all the collision property of cesium atom. Essentially close this chapter. All right. So now, after a few years, we can really provide you a new way to understand phase bar resonance, and also I think there are a lot of people, kind of precision measurement people in the audience here. Okay, so we can understand phase bar resonance the following way using the analogy from the light wave interferometry. Okay, interferometer. Okay, so you send a light wave, and it's a beam splitter. Okay, then you can measure the fringes. Okay, measure the interference between one arm, okay, and also the other arm. The two electric fields add, and they add constructively and destructively. Then you can see interference here. And then, when two particles interact at very low temperature, the behavior should be described by matter wave. What you have is also interference pattern, but it's an interference between the incident wave with the scatter wave, the forward interaction. Okay, and this is what for single molecular potential. Okay, single molecular potential, you can think about the matter wave. Okay, it's now interfere with itself. Okay, with the incident wave together with the scatter wave. And phase bar resonance now can be understood in the following: when you prepare two particles and then interact, okay, and phase bar resonance will occur when there is another potential. This potential can be supported by a different molecular potential with different say spin configuration. Okay. And when they interact, then the scatter atom can be trapped, can interact with this bound state, and they can go inside and scatter back and forth multiple times. And this is equivalent to an interferometer with one arm inside the optical cavity. Okay, and the weaker the coupling is, the longer the matter wave will be trapped inside the cavity and go back and forth multiple times. Okay, and it turns out this kind of picture provides has a pretty far-reaching application that you can use a phase bar resonance as a very, very sensitive probe to see how many wave function oscillation there are in this arm relative to the other arm. And one arm is in free space, an incoming wave. The other one really probes how many wiggles there are in the potential. Okay, and then how many wiggles there are inside the potential determined by two factors. Okay, the wave itself, okay, determined by the mass of the atom. Okay, that's a wavelength of the matter wave. However, the potential is determined by mostly determined by the interaction between two atoms, which is electronic. So therefore, how many wiggles there are depends on the ratio of the atomic mass to electron mass. Okay, and that is an important fundamental constant. Okay, so if we can perform this kind of matter wave measurement near narrow resonance with essentially high finesse, it turns out the measurement scattering can be converted into an extremely precise measurement on the mass ratio, electron to proton mass, the mass ratio. And that enhancement factor, okay, can be 9 to 12 orders of magnitude. Meaning, if there's any change of the mass ratio by one part per billion, it could lead to 100% change of the scattering length. Okay. All right. But phase bar resonance also have many other applications. After I graduated, I continued working in this field, and just to show that this, in one case, when you bring the resonance close to bring the atom close to resonance, the coupling between atom molecule provides the first provides the observation of ultra-cold molecules, and this is ultra-cold cesium-2 molecule created from the cesium BEC. Okay, and the pairing for bosonic atoms has been seen here. Pairing of fermionic atoms also lead to the molecular pairing in one regime, or the Cooper pairing in the other regime. Okay, and this result to get also realized in MIT and the GLOS group were considered top 10 science breakthrough in 2004. And another thing that Steve brought into our attention, okay, in 1999 about this the three-body collision resonance. Okay, unfortunately, that was a little bit too early because at that time we haven't really pinned down the two-body interaction. But after we understood the two-body interaction, we also have a very good starting point to look for three-body resonance. And this is a prediction in the, almost 35 years ago, and in the context of nuclear physics. But now it's been demonstrated, has been observed, okay, by phase bar tuning. Okay, and there are also other dreams where we haven't really realized. One of them would be, okay, whether it's possible optical cooling to a BEC. Okay, I think, well, hopefully in 10 years we'll have the next birthday party will be able to show some good news. Or, okay, another important application will be to see the quantum information processing. Okay, maybe in 20 years. I think there are many very exciting new physics branching out from the control interaction, as well as many other physics. Okay, based on availability of ultra-cold atoms. So we're hoping in many more future birthdays we'll be able to show you all the exciting results here. Okay, I'll go back to Vladan.
Thank you. That's Jamie Kerman, who unfortunately could not be here today. Just to finish up, eventually I did go back to magnetic microtraps, but that was only after I had my own group, so it took about 3 years, this short deviation. This is an example where we use a magnetic microchip to prepare the atoms in an optical resonator in such a way that we can reduce the quantum noise, or maybe more accurately, redistribute the quantum noise in such a way that we can improve precision measurements. This is an example where we use an atomic clock transition, and this is the so-called projection noise, which has to do with the fact that when you measure n independent atoms, each atom, upon measurements, decides randomly which state it is found in, which produces readout noise, a binomial distribution readout noise. And we have now realized a system where we have reduced the spin noise by as much as 9 dB below the projection noise limit, and where we have improved clock performance already by 3 dB and done some other improvements, so that I hope to very soon have an improvement of clock performance by about an order of magnitude with these techniques using microchips. Sorry. Yeah, I will not go into that. Microchip ideas can also be applied to ion traps. This is an example of a trap that we have built. This is about 1 millimeter across. We simultaneously confine ytterbium atoms in a magneto-optical trap and the ytterbium ions in an RF Paul trap. And we have been able to make measurements of the ion atom cross-section down to energies corresponding to a few millikelvin in temperatures. So this opens maybe possibilities to implant ions in Bose-Einstein condensates. Going back to Steve's ideas, to optical dipole traps, we have also realized the system where inside the single-mode hollow-core optical fiber, we have an optical field that can trap atoms, and we have used this in collaboration with Misha Lukin's group to do all optical switchings. We switch photons of photons, and we are already at a level where we can switch a few hundred photons with pulse of a few hundred photons. A lot has been said about Steve's character today. Well, time goes by, people change, especially under the influence of good and strong forces, and she's sitting next to him. So those of you who have known Steve would not believe, but I have personally witnessed Steve buying a Lexus. A pre-owned Lexus. And I understand that the battery was not quite as good as the one of the Fiat that you were able to purchase. In any case, Steve is not only a fantastic scientist and a fantastic sportsman, but has been an incredibly inspiring mentor and a true friend. Thank you, Steve.